Hello, and welcome to Materials Unlocked, the podcast where we take a look at the lesser-known subject of material science and try to unlock its mysteries. My name is Dr. Lewis Owen, and I'm a lecturer at the University of Sheffield. In each episode, with the help of some students, friends and colleagues, we're going to delve into a particular topic and hopefully unlock its potential. So in this week's episode, we're going to be talking about making the samples. And as always in these episodes, I'm joined by one of our current students. And this week, it is my great pleasure to introduce Wunmi Olukoya, who is a fourth-year PhD student now. Is that right, Mimi?
Yes, I am a fourth-year PhD student.
It's one of those things no one likes to admit the actual year they're in. It's, we're at the beginning of the year and the number goes up by one and you get that much close to the end and that much more terrifying.
Oh, gosh. Thanks for the reminder.
Sorry, I don't mean to put you on the spot. But so could you tell us just briefly about what it is you work on, what you study?
So I'm a materials girly, I'm a metals girly, and what I'm looking at is soldering. So it's something that most people have some kind of idea how it works, but I'm looking at replacements for lead-free solders and using that to join with silver.
So this is trying to make it more environmentally friendly by removing the lead from the solder. Is that the idea?
I think it's much more understanding the world without lead, because lead does make things work better. There's a reason why it's been used for like decades, but because of the environmental impact, we've had to remove lead. And we're trying to really just find out what that means and how to make the solder joints we do have better, especially for electronic applications.
Yeah. You mentioned for bonding to silver. So where is that primarily used? Or
the silver for my project came from heated windscreens. So there's a little bit of silver in heated windscreens for cars, but then that kind of expanded to looking at what actually happens when we join to silver.
Sort of more in general. It's often the case that in PhDs you start on one particular topic and then sort of meander a bit around, explore sort of adjacent areas and things. And did your previous degree, was it in material science or were you in another subject?
I'm material science and engineering to the ground.
All the way through?
All the way through. I did material science and engineering in Swansea, and then I did a placement or three rotations as a material scientist and process engineer. So
wow, yeah, material science through and through in your veins. But so when you were coming, I'm just interested, when you were coming to the end of your school career and thinking about choices for university, what was it about material science that particularly, attracted you to the field? Because I think for a lot of people, it can be quite a big jump to move into a subject that they've not done before and don't have much experience with.
Oh, I think it's quite funny because I think I didn't know what material science was, but someone challenged me to find something that had all my A-levels in. So I was doing physics, chemistry, maths, and fashion and textiles. And fashion and textiles was the one. I was like, yes, materials science. I don't so. But I'm really glad I did that because I think material science is like, we want to understand the whys of how things work, but also how we can apply that to things. And I feel like that's quite a broad thing to say with engineering or science, but I think, well, everything is material science, kind of.
No, but I think you're entirely right that particularly with material science, it has much more of that applied focus. And it's something that we've been talking about in a previous episode, was that sort of close overlap or close alignment with industrial problems and how we often need to understand that industrial problem in order to, make materials choices and develop a new material or develop an existing material into a material for a new purpose. So today we're going to be talking about making the samples. I assume for the sort of things that you're doing with solder, the samples that we're talking about are really quite small, sort of small little blobs of solder on the orders of sort of millimeters and things.
You're right. My samples are absolutely tiny, and
you've got to look like it's easy for you to lose samples.
Yes. Sometimes when I'm tired, I'm just like, right, I really need to be careful. But my solder blobs, my solder is quite tiny, and then I'm also looking at quite small samples or substrates itself. The silver itself is quite small, and really the mechanisms that drive solder wetting or spreading are in nanometers. There is such a small scale and such quick time frames that you have to be really, really careful and actually really understand what your data is saying. or what output is coming out of different machines, because it's quite fiddly.
Yeah, well, length scales is a very important thing in material science in general, but I think particularly with making the samples, it's something that I'm hoping we're going to explore a bit today, is the sort of length scales and the different length scales on which we work. So I think at that point it's a good opportunity to introduce the two specialists who we've got joining us today. So we're joined by two people, both of whom are Henry Royce Institute engineering leads. We're joined by Dr. Yunus Azakli, who's an engineering lead in materials discovering and prototyping, and Dr. Will Pulfrey, who's an engineering lead in thermomechanical processing. So Yunus and Will, welcome to the podcast.
Hello. I am.
Great to have you both here. So actually, just following on from Mimi, perhaps you could tell us a bit about your backgrounds and a bit about what you do in your work at the moment. Yunus, do you want to kick us off?
Yeah, I can do. I'm a material scientist from tip to toe. So I studied material science in Turkey. I did my undergrad, and I did my master's and my PhD in Turkey. Then my PhD, I worked on nickel-based alloys, manufacturing nickel-based alloys, basic compositions, but the idea was to investigate oxidation, high-temperature oxidation properties, behavior of those, special bespoke metals, really. So then obviously the work that I did throughout my studentship and my PhD opened me the door to UK.
Yep.
So I got my job here in 2018, and since then I've been working here as an engineering lead for Royce.
So you've always been more on that sort of applied side. You mentioned manufacturing during your PhD, so you've always had that interest of making things and doing stuff, practically. Is that right? Or?
Yeah, that's correct. I'm not afraid of making my hands dirty. I'm happy to go home with the dirty clothes, but a full mind, and I still keep thinking of the work that I'm gonna do next day. So I'm always kind of, keeping my mind busy out of the work so I can do some practical work when I'm at work. I think this is because my father is also an engineer, so we always observed him, fixing things, breaking things. And I think Mimi mentioned about soldering. I started soldering when I was probably 10 years old.
Yeah.
Because I wasn't doing something proper, but I was trying to hold the soldering iron and the soldering material to kind of bind things together. So my brother and I, myself.
And so you're always destined to be an engineer, and materials
I think so.
Just sort of appeared out into the...
And the interesting thing is, even my brother is also a material scientist. So.
Oh, right, okay. A very materials family. Gosh.
Yeah.
I don't think I've ever come across a family of material scientists.
No, not my father, though. My father's an electronic engineer, but my brother and I don't know how we picked. I think it's my father's impact on our education, I think.
Yeah.
Which I'm quite grateful, really.
Oh no! I think it certainly has a big influence, that thing from your parents. My mother is a physics teacher, and I think growing up, I often would be able to ask and have questions answered along those lines. And as you say, from your point of view, like seeing someone working on these problems in a very practical way has obviously set you on that path towards sort of an engineering discipline and material science. What about you, Will? What's your background?
So I'm a relative newbie to material science. So my background is mechanical engineering. So undergraduate, master's, PhD, and then I've started this job around 2 years ago. So I've not really fully appreciated the world of material science until I've been in the job and then realised how overwhelming it actually is. I've gone from, identifying the difference between basic materials to then understanding, well, what are the different compositions and what are the benefits of changing those compositions for different applications. So yeah, it's come on thick and fast, but absolutely loving every minute of it. It's brilliant.
So in your mechanical engineering degree, did you have like a module on materials, or was there no materials?
Yeah, so it was, if I can remember, we definitely did some basic materials science modules, but that was it. It was basic.
It was like surface level sort of
stress strain.
Good stress strain curve. Yeah, it's often plotting a stress strain curve.
So that's as far as it went, really. But thinking back now, it was because I was part of the former student team, so there was lots of design, and then the selection of materials was we kind of just chose it because it worked rather than really understanding why. So I remember vividly that we used a 6000 series aluminium for the uprights that we used, and that I didn't really know why. It was just kind of like, that was there, it was available. So we used it, but now having actually working with the different alloys, you kind of like, that's why we chose it, just through chance and opportunity. But yeah, it's brilliant.
And I think that's the one of the really interesting things is that why. And I think there's a lot of misconception out there that we know sort of everything about materials, but there's still so much for us to understand about why it is that particular thing makes that material have those excellent properties in in metals, in ceramics, in battery materials, in whatever we're looking at across like a whole range of different things.
Well, one of the really interesting things that I found, it was maybe about 6 months ago actually, we went to a forging company near Walsall, and they'd been producing some offshore pieces. They were creating these parts, and they'd then scrapped at least 50% after forging. And it was only through conversations afterwards that they realised that these parts that they were forging, 50% of it was only needed, and the other 50% wasn't needed, but they were doing the whole spec to the whole part, so they're getting rid of it. But anyway, they were using some stainless steel material, because that's what they kind of had the most knowledge on.
Right.
But then what we came to them with is a titanium, and they were a bit reluctant to using this titanium because there's not as much information surrounding it, because it's for offshore applications. They need to be really sure that this is going to work in the actual application. But they found that, I think it was for every part that needed to be forged, it required 10 blows, and that the stainless steel needed to be heated up to like 1200 degrees. But with the titanium, they're using it at 900 degrees, and it took 2 blows to get the same part. But not only that the titanium part had far superior characteristics for the actual application. And they've been creating this part for years and years and years, and just hadn't thought to
This sounds like a fantastic win-win-win.
Yeah.
Not only have you got a material that ends up with better properties, but you're using less energy to actually create it and all of those sorts of things.
And I think it's because previously...
Very productive trip.
Yeah, absolutely. Yeah. But I think because previously they'd always associate the titanium was so expensive. So to buy that in as the raw material, they were kind of reluctant to even start looking into that.
Yeah.
But because we'd produced the titanium through swarf, through the field assisted sintering technology route, we're now taking this waste product, creating the billet, and then forging that. So out of nowhere, we've now got this waste stream material that can be used to create these parts that are superior to the parts they've been making for decades. So now it's it's more available than it would have been, say, 10 years ago at least. But yeah, it was very productive in terms of a trip.
Sounds fantastic. So today we're talking sort of in general about making the samples. So in our first episode where we talked about the materials design cycle, we thought about, how we might go about defining the problem and then predicting various properties of materials. And once you've sort of designed a material or thought about the adaptation of a material for a particular purpose, the next thing is obviously to make a chunk of metal, in this case, and actually test it to see what the properties are. But that making process, it sounds, I've sort of just gone, we just make the samples in a sort of throwaway way. But it can be quite a complicated and involved process sometimes, making samples, particularly depending on the scale and the amount and, the various elements that go into it. So Yunus, I think you do quite a lot of this, of sort of, making things at sort of various scales. So perhaps we could start there, actually, thinking about like, when people are looking at making samples, what sort of scales are we working on for sort of making of samples?
We can tell by the volume, I think, from 1 cc, maybe less than a cc, to 1 liter.
Okay.
So the existing equipment we're gonna hopefully soon have another equipment online, which will be able to do about 2 liters of metal ingot, which means nearly around 20 kilos of steel, maybe something like that.
Yep.
So depending on the equipment we have downstairs in the research center, obviously we can do fine ones. Some equipment can do a minimum. It needs to be more than something. So we're using different heating systems, induction heating or arc heating. So for example, with the induction melter downstairs, we usually do 5 to 10 kilos.
Okay.
It's a good size, brings you good size of samples and good amount of samples in there. But because of the coil size and the turns and everything, the setup, we cannot do too little because the induction won't really see the metal and then heat it up, so we won't be able to melt it. So we've got some limitations, but when it comes to size and composition, you need to be careful, obviously, on how to pick the right method to produce the metal. So we can't use all the processing methods to produce all metals. You need to be careful with that.
Yeah, so I suppose the first thing is what are we trying to, do with our sample once we've made it? And for some people, they'll just need, a gram or two of metal, whereas for some people they'll need the 5 or 20 kilograms. So I know certainly for some of the PhD students who I supervise, if we're trialing a new metal, we'll use something you mentioned earlier, the arc melter, where we'll just melt up, a small, we call them buttons often, like, a small amount of 10, 20 grams or whatever that we can then do some basic tests on. But then sometimes you need that bigger chunk. And obviously as we scale up, there are additional challenges associated with it, and possibly see different things or effects, right?
I mean, especially if you do a small sample, I mean, you imagine for an atom to diffuse 1 centimeter from one corner, one side of the sample button to another side. It is so easy. But when you're making a huge ingot, then you can talk about segregations and inhomogeneous sections within the alloy.
So you can end up with sort of one side being iron and one side being chrome if you're not careful.
Yeah, definitely. You have to so, for example,
make sure you get mixing all the way along.
Brass-like alloys, for example, they have zinc in them. You may see zinc separation depending on how you cast it, how you solidify it, things like that. So the bottom of the alloy might be rich in copper and some other elements, but top bits might be rich in zinc. So these are all the factors that you need to really consider when you cast a metal, or, depending on the casting method or depending on the mold material that you use to produce that ingot. But in small scales, you usually don't have that issues because, we're talking about a very tiny button, say a centimeter in diameter, and everything can move to the other side and mix up nicely in such small scale, really.
So do you have a favorite scale? Do you prefer to make little ones or very big ones?
I mean, I like when I use the Vim, the glow. William likes that too. The glow of that huge metal at 1500 degrees Celsius, 1600 degrees Celsius. It is a small scale. If the industry people will listen into this, they'll say, what the hell? It's just, I can hold it probably. They'll say, for us, because research institution, obviously, it's a good scale. And I respect the metal that is looking at me. You know what I mean? It's nice, shiny. And there's lots of energy stored in that. So it feels a good energy to me when I pour that nice metal, and then the other pleasure is that's going to be someone else's study material. So it gives me the real pleasure. I'm going to be useful for someone else. I'm going to be a tool for someone, so they can go along the way. You know what I mean? With the material that I produce, I think it's the real pleasure when I produce the metals.
But it's always interesting looking at it, isn't it?
William is the curious guy. What's that going to be then? He always says, are they going to give the results to us? What is the tensile stress? What is the hardness of it?
But I always find it so fascinating, because to me, the analogy I always use is to make bread. Getting your raw ingredients, is putting it inside, is mixing it together, and then making the bread or loaf afterwards. But the amount of slow-mos I've got on my phone of the metal and it bouncing all over the place, it just looks fantastic.
Oh, well, we might add some of those to the show notes so people can have a look at some short videos of some of these things, because they are very beautiful to look at, as you say. And I think the baking analogy is a really good one. At the end of the day, we're essentially, making this material in the similar way that we might bake. We have to think about the ingredients. We have to think about the order in which we add things, the process of doing things.
Definitely, yeah.
So one thing that you mentioned earlier, Yunus, was that different elements might have different challenges associated with them.
Oh, yeah.
I wondered if you could talk a bit about that and some of the challenges that you face with different elements.
Yeah. So when someone comes to us with a certain composition, it doesn't matter. Size doesn't matter, for example, at the moment. What I have a look at is probably the short periodic table, right? I have a look at the, obviously, most of them I have it in my mind now, but I still check myself. The melting temperatures, the very basic I'm talking about, and the evaporation temperature of the elements. So something that you also need to consider is the reactivity of the metals. So, for example, you were making a nickel-based alloy. It's industrial practice or practice downstairs. It is the same thing. So you don't want to put the reactive metals in the crucible from the very beginning. The metals like aluminium, titanium, hafnium, or yttrium-like metals, they like to react with everything in the environment. If air, maybe nitrogen in the air, humidity, oxygen, we remove them, most of them, by using the vacuum system. That is fine. But there's crucible. They are mainly made of oxide-based materials. Some of them contain alumina, silica as a binder material, or to give them some thermal shock resistance, things like that. So most of those metals will tend to react. Even aluminium oxide, metallic aluminium will react with aluminium oxide at high temperatures. It's oxide. Titanium will pick up loads of oxygen in it, and it won't show a sign that is oxidizing, but it will dissolve loads of oxygen inside. So in the end, you'll pour the alloy, make the ingot, and the chemistry will say, oh, the oxygen level is 500 ppm, which is way over the specs, really. So there is a sequence that you need to follow when you make special alloys. So, for example, again, for volatile elements, if you're making a manganese-rich steel, so they are lightweight steels. They contain usually, obviously, iron as a main element, aluminium, manganese, and carbon. So, again, in a system, if you try to make that alloy under vacuum environment, it means that you're going to evaporate most of the manganese out of the system, because evaporation temperature is 2,000 degrees Celsius at 1 atm. If you're slightly under vacuum, it's going to be 300 degrees lower. It means it's going to boil up nearly.
But that's what always just threw me, not really thinking that a metal could be evaporated. Like, I remember that one of the first days that I started, Yunus was showing me, he was casting whatever material it was, and you were trying to break down a refractory metal, and you're like, oh, this is like 3,000 degrees that it needs to, before it would melt, or something ridiculous. And you're like, oh, did you see that green flame? Did you see that green flame? I'm like, yeah. And it's like, what's that? It's like, that's evaporating metal. I'm like, what? How does that work?
Melter then, yeah.
Yeah, it just blew my mind. Just didn't really... Yeah, I never really appreciated it until you kind of get into that work.
I mean, I came from a chemistry background, and there, when you're doing the experiments, you're holding it at sort of 68 degrees Celsius or something for a long period of time. And then I came into the metals world, and it's suddenly, oh, we're going to heat this at 1,200 degrees. I'm like, what? The scales of these things suddenly changes entirely.
Yeah.
But yeah, so coming back to what you were saying, Yunus, you mentioned earlier sort of the choice of mold material. And I suppose that's then with this reactivity, that's something you need to consider, is whether your material is going to react with
with the crucible,
the crucible.
With the crucible,
so, yeah. And then picking up on one other thing you mentioned was specification and things, which, again, coming from a chemistry background, often, when we have sodium chloride, for example, as salt, we have a sort of exact balance because of the charge in the system between the number of sodiums and the number of chlorines. But with alloys, when we're melting these things up, you can have quite big changes in these.
Doesn't need to be stoichiometric.
You don't need to be stoichiometric. You can have, all sorts of fractional bits. So I suppose one of the real challenges for you is creating that process where you end up with exactly what you want to get, or within a certain, there's a sort of tolerance for a lot of these things, a region you're working in, is that right?
Yeah, true. Especially for steel family, it is this little bit easy to do. So, for example, nuclear grade steel, chromium content can be between 8.5 to 9.5. So you can do that quite easily. But there are some elements that you need to be quite careful with, like nitrogen in that steel, so carbon content. But it is, when you're into that, you realize it's not really, really, really hard. But obviously you need some time to understand how things behave. Obviously, part of research is reading. You need to be reading and refreshing your knowledge continuously. And in the papers, we can't always see the practical information. So you need to kind of build up your own practical way to make things, which can be a kind of sad sometimes, because you fail these experiments in the end. If your approach is kind of scientific and careful, it shouldn't take too long to manufacture an alloy, especially if it is manufactured elsewhere in the world. You know what I mean? We've got the technology downstairs here. I mean, not all the melting capabilities maybe, but we've got some and good portion of it. So we can produce most of the alloys that people can do outside the world. So it is kind of giving us the opportunity to, okay, let's do it. We can try it. We can do it. It's giving us the boost for us downstairs to try new things, really.
Yeah. And I think that's where the real, as you say, it's the sort of the development of that skill and the sort of art of, understanding how these things work and making those tweaks. And as you say, experimenting and trying something by a certain process and then adapting that process to make sure that you're obtaining exactly what you're hoping to get out of the situation to begin with. So once we've sort of got our lump of metal that we've sort of, cast, and we've made this thing, we've melted it up, and we've got the chunk. That, I think, is very often when it gets handed over to sort of you, Will, to do some sort of other things on. And we mentioned earlier this sort of thermomechanical processing in your title, which is probably something that people haven't sort of thought about or necessarily come across before. So could you explain a bit what thermomechanical processing is as a sort of idea, a concept?
Yeah, absolutely. So like thermo, so hot work, essentially, and the mechanical side is using machinery to generally manipulate or process that material. So thermomechanical processing is hot metal work for what I do. So one of the machines that we use is a hot rolling mill. So just a general rolling mill, but it's quite sophisticated in that it's really good for the research purposes, but Yunus will often cast me ingots at about, say, 100 mil cube, which we then process because people will typically want that reducing in height. So they've got a longer piece of material which they can section up into tensile specimens, for example. We typically process things from like the fast or field-assisted sintering technology. One of the things that we've been doing recently is commercially pure titanium. So again, we've been taking this swarf or this waste product, fasting that down, which is, so field-assisted sintering technology is essentially a giant hot hydraulic press. So we can process or make this into a solid ingot underneath the melting temperature by applying this pressure as well. And then we will roll that down to, again, so one of the things that we're wanting to do is to take these samples and forge them, but the sample that's created on the fast machine is 250 mil, and the forging sizes that we need is 275 mil. So we've had to section this diameter or this pie up essentially, and then roll it out to the specified length to make sure we've got the right thickness so we can then generate it ready for forging.
So this process of rolling, you've literally got two big cylinders that are just pushing your metal down to shape it. So is it primarily is the use of this thermomechanical processing in order to get it into a particular shape, or does it have materials advantage or disadvantages associated with it as well?
It is varied. So if people want a specific strain rate to kind of build the texture of that material, or they just want a change in mechanical properties for after rolling, or people just want to change the shape, which they'll then heat treat to get back to an original state in terms of the mechanical properties. But one of the biggest challenges that I didn't really again, appreciate until I started doing it is the kind of sample size. So in terms of Yunus's favourite sample size, mine is always bigger, the better, because it retains that heat. Okay. So we've got from those buttons that you were talking about, or maybe slightly bigger. By the time we get that out of the furnace and we put it over to the rolling mill, it's lost its heat. But then you think, well, let's just heat it up more. So by the time we get to the roll, it's at the temperature we want to roll at. But the further you heat it, the more oxygen it picks up, and then it becomes more brittle and it's going to crack and fail. So bigger samples is always better from my mind because it will retain that heat and we can process it a lot more before we have to then reheat it.
So why is it better to have it at the higher temperature for that rolling process? What are the problems if it cools down too much?
So as we increase the heat in the material, the yield stress or the flow stress becomes lower. So it's easier to manipulate that material at a higher temperature.
Right, yep.
So typically for like steel, we might be at like between 900 and 1200 degrees where it flows really well. As soon as we start reducing temperature from there, it just gets harder and harder and harder, which puts more pressure on the rolling mill and it's more likely to crack because so far the rolling mill has not struggled at all. So it will be the material that fails before the rolling mill. Hopefully.
So is it like, I'm imagining when you make pasta, you have those little like 2 little cylinders or whatever that like squish the pasta itself. So would if we're saying about cracking and saying about different temperatures and that, would it be like when you have fresh pasta, it's lovely and ductile and quite springy, so it goes quite happily. But then when you leave it out to dry, or say you've forgotten it in the fridge, it starts like cracking on the top surface and that. Is that kind of what you're saying happens with the metal?
In fact, one of the things that I always try and relate to, again, is baking. Not that I'm a good baker at all, but it's like a rolling pin. Do you know, when you just roll out the bread or whatever, and you'll start to kind of get edge cracks because the moisture is kind of segregated from that side, so it's not as pliable and becomes more brittle and then starts cracking. But I guess that's not really relatable to the metal because it's not so much got moisture in it, but similar principles in the way it operates.
You may think of rubber.
Rubber, yeah.
If the temperature is high in the room, it will extend much easily. Or think of the copper wires, electrical copper wires, high voltage copper wires and stuff, or in aluminum. It doesn't matter, but the metals, they kind of extend because they expand with the temperature, obviously thermal expansion, but also think that they may get softer if the temperature is, say, just imagine this, 100 degrees, 200 degrees, it may even sink with its own weight, you know what I mean? So maybe even that is not the real example, but when the temperature is higher in a material, the distance between the bones will be larger. So it means that interaction between the atoms will be lower. That means you can manipulate that material much easier. I mean, in a basic way, you can think the spring is much softer. You know what I mean? So you can do whatever you want with it. High temperature is the better.
Yeah. When I started, actually, it was Prof. Martin Jackson was kind of saying, rolling's a bit of a black art. And I was like,
oh, yes, it is.
Like, okay. And the more I've done, the more I can appreciate that term because you've got the temperature, you've got the geometry or the size of it, the kind of how you're introducing the material into the rolls. Fortunately, being in this environment, we can fail all the time because if we're not failing, we're not kind of pushing to those limits of what we're trying to learn. So I failed a lot, especially initially when I was trying to kind of understand the capabilities of the rolling mill. And trying to get a flat sample coming out initially was just like, it's just not happening. It would banana up, it's going down, it's wavy from side to side. But then once you start to understand, well, actually, the temperature distribution of the sample is going to be different because we're bringing it out in air, we're placing it on the table. The conductivity of the table, which is metal, in comparison to the air is different. So we've got a temperature distribution of the metal. So by the time we introduce that into the rollers, one side is hotter than the other, so one's going to flow much easier than the other, so that's what causes these bends. And just simple things like that,
So just give us an idea, how quickly is this going through the
Oh, yeah.
Like,
well, this is the thing that always, when people come and observe, is the most underwhelming part of it because
it's done so quickly, is it?
We'll say, it's like, well, we'll need about 4 hours to 6 hours to do that. So by the time we heat it up and we're waiting, and then you put it through the rolls, done.
So, Lincoln, you've missed it.
One of the things that we've had to work around as well is that the rolling mill itself, it would so we can monitor monitor pressure, temperature, roll speed, torque. So we acquire all this data. And the frequency in which it was acquiring that data was every second. So some of the samples, you're looking at the display, and the pressure's there. You'll process it, and the pressure just stays the same because it's going one, because the sample's gone in and out before it's even registered it. So we've had to create our own software to go into there, so we can acquire the data at a much faster rate, so we can actually see what's going on.
So I suppose then with as you say, you've got all these variables, and picking up on sort of Mimi's analogy with pasta making. I love making pasta, by the way. But, on those pasta rollers, you have a setting where you gradually decrease the width of the rollers.
Okay.
And I suppose with this, there's a question, as you say, about the sort of the pressure with which that you apply, how quickly you sort of are aiming to reduce that sample height, whether you're trying to do sort of high pressure for a short amount of time or do lots of passes of sort of low pressure. Are those sort of things that you have to sort of play with and try and optimize? Or
so one of the things I didn't again appreciate coming from a mechanical engineering background, how many mechanics? How much mechanical engineering would be required? So solid mechanics. So understanding like the friction of how the material interacts with the rollers. So our limitation is basically the diameter of the roller, which is 200 mil. So there's a point at which the friction will bite that material. So that kind of governs our maximum reduction. So I'd say that the biggest reduction we've done is on one pass, I'd say is about 6 or 7 mil. Any more than that, typically the material won't go in because it can't bite. It just won't take it.
Right.
But
it's
some
jams in the machine.
It literally won't do it.
Okay.
You could try and push it as hard as you like. It's just like, no, we're not going in. But some materials, so say aluminium, pure aluminium, you could quite easily deform that, especially hot 7 mil, no problem. But if you had a commercially pure titanium or any alloy of titanium, did that cold and tried to do 7 mil, it would be a completely different story. So we have to do multiple passes dependent on the material, dependent on the temperature, geometry. But typically we try and do as many passes as we can before overworking the material. So we need to, depending on the starting thickness and final thickness, we basically want to get there as quickly as possible. So we don't want to keep that subject to heat, because typically the longer it's seeing heat, the more oxygen it's picking up and creating more oxides. So we want to do as many passes as possible before we overstrain that material. And if we overstrain it too much, it'll then break or fail. So we have a rolling schedule where we might do 10 passes. So we go from, say, 80 mil down to 50 mil, then back in to reheat, let the material recover, and then do it again. So maybe 3 different schedules. Yeah. But during that time as well, we'll have different roll speeds to help with the strain rate. Because if at big, thick samples, we typically roll slowly, but then at thinner samples, we'll do smaller reductions but faster speeds. So it almost doesn't let the material react and comes out again straight. Because the thinner you go, the quicker it loses heat. So that temperature distribution again, it goes really, really quickly. So we have to process it as fast as possible before the temperature can change, and then you get all sorts of mangled things coming out. So that's why it's a bit of a black art.
I was going to say, it just sounds so complicated. The fact that, every time you're putting it through, you've got a new geometry, essentially a new material with different alignments, different amounts of oxides, so what you did on the previous run, you may now have to change for the next pass of the material going through.
Absolutely. So it's fantastic from my perspective, because no job is the same.
Yes.
So even down to different steels that Yunus will cast, it's a different steel, so it will behave slightly different in terms of its yield strength might be more, or the temperature. It's completely different all the time.
As I sort of mentioned earlier, sometimes those changes are actually what people are looking for, right? In terms of you're doing this thermomechanical work on the object in order to give it certain properties, not just get it into a certain shape, but to give it certain, strength properties or a certain alignment of the crystals or whatever it is that you're trying to get within your material.
Yeah, absolutely. Because so when Yunus casts a sample, it might be full of all these different pores throughout the casting, and the grains are typically going to be quite big. But through mechanical processing or thermomechanical processing, we kind of reduce those grain size, which gives it extra mechanical strength, and remove those porosities, which are essentially voids within the material. So afterwards, the grain structure is a lot more coarse and lacking of void, so the mechanical strength shoots right up.
So you talked about fast before, which is sintering, basically joining squishing things so much at such high temperatures they join together.
Yeah.
And you're using swarf as well.
Yeah.
Was one of the things you said. So I'm assuming the swarf isn't uniform. Everything is kind of mixed and matched, different shapes or maybe different lengths. So is that why you do the rolling afterwards, to squish out the pores even more?
Not necessarily, actually, because actually with the fast operation, because you're applying a pressure while heating that up. So with casting, you'll get these pores, as Yunus might correct me, but as things kind of evaporate within, or
it can be something to do with the flow. You don't always get laminar flow depending on what kind of funneling system that you use. You know what I mean? When you pour the metal, if it is not vacuum, there will be some gas entrapment inside the alloy, because the alloy, I use permanent mold. It is steel mold. It will suck the heat out of the metal quickly. And when the metal cools down or near solidification, it becomes sluggish. And then those bubbles, argon pockets really inside, cannot climb up to the surface and then get entrapped. So William gets rid of them by rolling, by mechanically deforming those gaps, really.
But with the fast, so as you can imagine, the swarf is basically a bowl of cornflakes, for example. But because we're applying that pressure on top, we're crushing that down and down and down, but also applying that heat, so it starts to diffuse and bond together. There will be still some porosity within that sample, but typically it is fully consolidated. But if we are then to roll it afterwards, we typically, you never eliminate everything, but you can obviously reduce that porosity.
And you talked about texture.
Yeah, so...
What do you mean by that? Because the texture of something is how something feels, but I don't think you're talking about the same thing.
So the texture is basically orientation of the grains. Every grain has a different orientation, and dependent on the orientation, which can be manipulated with rolling, so you basically force the orientation of those grains to a certain way, it will have a mechanical property difference in terms of the different ways. But for this application that we used it for was to stop radiation going through the material. So if you have this texture in a certain way, it actually stops the radiation going through the material. Whereas if the grains or the texture is in a different orientation, the nuclear or the radiation can actually seep through the metal. So the texture is the orientation of grains.
So it's like if one grain wants to look left and another grain wants to look right.
Yeah.
It's literally just been like, right, when lots of grains look left, it does this.
Yes.
When lots of grains look right, it does this. So we don't want that, so we're going to change it.
Yeah, so my rollers make them all look left.
Okay. By force.
Depending on the material can be easier or more difficult, right?
Yeah.
Because, some materials, these grains that grow will have a particular shape or orientation. I often think of it like, if you've got a jar containing toothpicks or something like that, it's very easy for all the toothpicks to line up in the same direction.
Yeah.
Whereas getting the toothpicks to all go randomly is quite difficult.
Yeah.
So actually sometimes the material goes, I'm gonna align everything in the same direction because it makes it easier. And particularly if you shake a jar of toothpicks or something, they'll all sort of flatten in that same way. But there are lots of examples where we've got this. If we can create that alignment of things, it can help to change the properties. And thinking about that level of the microstructure level, so this is where we're on the 10 to the minus 6 of a meter, a millionth of a meter level, and how that the properties on that level affect the overall material. So, for example, if we think of crystals in a turbine blade, people have been looking at for a long time, is it better to have lots of different crystals that are all randomly oriented, or is it better to have long crystals that are all in one direction, like columns, or is it better to just have one big single crystal? And in fact, each of those gives the material a different property. So, and, by the manufacturing process, we can, begin to affect that and sort of build in properties of our material based on how we align those crystals.
And what is the answer to that? Because people often talk to me about turbine blades and
So with the most turbine blades that we have now, that we have these single crystal turbine blades, because actually it improves the long-term creep life of the material, so how it deforms over the long period. So actually these things are grown by a very complicated method where you have to form this sort of single crystal that's grown up. But it's, I think these examples all help to highlight or demonstrate how the manufacture that we do has such a profound effect on the overall component. And there's that sort of understanding that we have to link between actually, what we're doing in the lab and the material that we make up, and then how that level of structure is affected by the mechanical processes that we're doing in the making of the sample. And actually coming back to, something that we were talking about earlier with Yunus, of the sort of the melting of these things, I often think, when we're designing new materials for something like an aerospace application or something, any number of applications, but we might try and make something that's, particularly strong or able to cope with particularly high temperatures.
Yeah, light.
But then the problem is, we've made something that's got a particularly high melting point that's not going to melt because we don't want it to melt in our engine. But then the question comes, how on earth does someone like you, Yunus, actually make the thing? Because we've made it so it won't melt, which creates a new challenge for you, or for you, Will. If we've made something that's particularly strong, it makes your life that much harder because, now it complicates that process.
So I've got a perfect example for that, actually. So one of the other machines that we kind of run is called a continuous rotary extruder, and basically it's a wheel that turns with a tapered part to that. So as you put the material in, such as you could put powder or kind of chopped up wire, it will then follow the wheel round, following the taper until it gets tighter and tighter and tighter. It then puts a lot of heat in, generated by friction, and then hits this part called the abutment. So it just hits like a perpendicular point and then forces it through a die. So this machine was created for a production life and to produce copper and aluminium. But obviously, as we're researchers, we're looking to adapt that for titanium. So now we're taking titanium and trying to, or harder materials actually, but trying to process that with steel is very hard, because we've now got this steel that's trying to process the titanium, and it just annihilates this abutment, where with copper and aluminium, it processes it absolutely fine. It could produce it all day long. But yeah, so absolutely, in terms of, you create all these fantastic alloys, it's like, well, we've come up with this fantastic new alloy, and it's so novel, and it's like, okay, well, how do we upscale that? How do we now transition this from research to actual production where it's actually going to benefit people?
Upscaling is a dirty word. I don't think we're allowed to talk about that, because it seems to be like one of the main... It's probably why we're still here, because if every bit of research could be upscaled easily, then fine, we could all go home.
True. Yeah, I'm not sure how you feel about that.
I feel so sad about it. Yeah, I mean, there are some examples that I can give. So again, for nuclear applications, obviously high melting temperature and so on, tungsten-based alloys are so popular. But when it comes to alloy, for example, tungsten with a lower melting temperature element, like, say, I don't know, iron, vanadium. Melting those together. Oh God, you can't.
Even something like a brass. I seem to remember that the copper has a much higher melting temperature than the zinc. And the
volatilization
so the zinc just wants to become a gas before you've even
melted the copper. Melting chamber, it was all snowy white or grey, let's say. It just literally, when I introduced zinc in the bath, because again, as I said in the early stages of this conversation, you can't put everything in the very first stage, because you will lose them. Some will evaporate, some will react with the crucible and so on. Zinc is such a metal. So melting temperature of the rest of the alloy is 10,000 degrees Celsius, but zinc will operate at 700 degrees Celsius. So we're talking about literally boiling metal. Like William is going to get surprised, but it's literally boiling, like boiling eggs and water. What I did, I remember it was a month ago before I went for holiday. Oh God. When I introduced the metal, it literally exploded inside the system. So there's nothing wrong with it, right? So if you guys are listening, if our DSO is listening, it was in the chamber, so I was all secure. So it literally ejected some of the metal out. It was like a volcano explosion. But then, okay, it reduced the melting, it reduced to bath temperature, obviously, this cold metal. Then things at least dissolved in the alloy. But it is a good challenge for people to add. What I would do if I had a pressure chamber instead of a vacuum chamber, that would be so cool, right?
Yep.
I don't have. Maybe I should ask some people. Again, for tungsten-based systems, so tungsten melts at 3.5 degrees Celsius nearly, and vanadium evaporates at 2.8. If I'm not wrong, people can correct me after that. 2.8 degrees Celsius or 2.9. So what happens is energy is consumed on the favorable reaction, which is the evaporation of vanadium rather than melting tungsten. So you're literally getting rid of vanadium or iron, whatever, in the system, which is the minor element. People wanted to have a solid solution system, really, but it's not the way to do it. Then we've got an SPS system, right? We've got a solid state sintering method which you can mix up powdered metals. Then you can easily apply heat and pressure, which will then cause it to diffuse much lower temperatures rather than try to melting them by applying crazy amount of energy, and by getting in the end you get nothing. So method choice is so critical when it comes to process. Very kind of not unknown, how can I say? I don't know how to define it, but exotic metals, especially exotic materials.
Yeah. And I think it's one thing that we just sort of, in many ways, take for granted looking around us. Metals are so ubiquitous. They're used sort of everywhere around us in the world. And we don't take time ever to stop and think about actually how that metal has been produced and the amount of work that's gone into first of all, extracting the raw elements, something we haven't even talked about or thought about. Yeah. And then once you've got them, how you melt it up, how you actually make just a block of it, and then how we go about shaping it or working it or applying something to it in order to get the properties that we want. And there's a huge amount of work that goes into every one of those stages for even something as simple as, one of the cans that we've got sitting on the table or something.
Yeah. One of the interesting things I actually found from starting to work here is because we often get external people coming in. So we've had rolling mill, not manufacturers, but people that manufacture steel products, and they've come to us to do work. And in my head, I'm thinking, we've got people that have been rolling steel for probably 100 years. They're experts in their field, yet they're coming to us to do some work. But one of the things I hadn't appreciated, that they're doing typically one material. They're doing the same geometry over and over again, so they've optimized that particular process. But if they need to make any changes to that steel because it's going in a different environment, that they can't then just stop the production route and be like, right, well, we're just going to try this different material, because they start losing thousands and thousands as soon as you stop that process. So they can then come to us and kind of take out those, look at the research needs that way on a smaller scale, but then we can try and optimize that process so that give them some confidence that when they try to then upscale it, they've got a head start going forward. But I always thought that was pretty interesting, because you had a casting firm over, didn't you, recently?
Yeah, I produced some metals for them. So you imagine a company that manufactures and sells worldwide, and they just need a tiny amount of alloy, tiny for them, but it's good size for us again. Good size that William and I like, so it's around 10 kilos. For example, obviously for them it can be so hard to manage a tiny melting equipment, again tiny for them but huge for us, 50 kilos so with capacity. So it is hard and expensive for them to literally run one equipment and make some bespoke alloys, but that's why we're here, right? So we're here to kind of try new things and even to make some bespoke pilot scale alloys, obviously using our knowledge and using our capabilities down here. So it is good for us. We're learning every day.
Yes.
As William said, there are things that we try, same alloy, 1 year later, okay, I've done this earlier. So have a look at my note. Okay, these parameters are right. This amount of extra elements that I need to put in because it's oxidizing or it's evaporating, things like that. But then that's not fun. For me, that's not fun, really, making the same stuff.
Yeah.
That's why probably we chose to be here.
Yep.
You know, in this building or in this work, really, because we're trying new stuff.
If you think about all the different applications, we go from automotive one day to nuclear, aerospace, defence.
Blowing our mind in a good way.
Yes.
Yeah, in a good way.
Constantly changing with constantly different materials, isn't it? So
yes, it's great fun. Great fun.
So, Will, are you a materials scientist now? Do you classify yourself as a materials girly?
I don't know enough to say I am, but...
do you deny it?
It's way more interesting than I ever thought it would have been. Because, so from my background, whenever I would design a rig or design the components, you would think, right, okay, what do we need to make? So you come up with a design, but then you're like, well, what material can we make this out of? So then you have to almost change your design based on the material you've got. And then you're like, okay, let's make it out of this material. And then it's like, you make this fantastic looking part and it's made out of this, I don't know, some kind of titanium. It's like, right, that's what I want. And it's like, yeah, but how are you going to manufacture that? It's like, oh, yeah, okay, well, let's machine it. We can't machine that. It's got too many different angles or the geometry is all over the place. Okay, so we have to... So the material kind of dictates so much, and that's basically a starting point. Every single component that's ever made, really. So from that perspective, maybe I'm all materials.
Love to see it.
Well, that's been brilliant. Thank you all so much. Just before we wrap up, are there any final thoughts that anyone has? Anything that they would like people to know about making the samples in general, or just about material science in general? I don't know, Yunus, if you've got any final thoughts?
When I started studying material science 18 years now, I think. I'm an old person. I didn't know what it was. But then, like William realizes now, you understanding a lot more about the environment, the things you use daily and how they're produced, how useful they are and how hard to, sometimes produce that stuff. I mean, every day we're using our computers, for example, but the technology in that we don't appreciate. So as a material scientist, so if you say working on, as a material scientist, if you're interested in producing chips and stuff, how PVD systems work, this all different ocean, you know what I mean? It's all great fun to do. What we're doing is a little bit dirtier, but still, how to say, we're learning every day. And for people who are curious, like William, I like that. That's the thing I like most on William. He always wants to know more and learn more. So that's the way to improve anyway. So we're learning every day. It is great fun, and we're doing practical stuff, and we're being useful. That is I think the most I get out of this, really.
Yeah,
because I think if anybody's ever considering kind of materials route and think they're going to be kind of tunneled down this one path, it's just materials. You're not just looking at materials. You're looking at how things are made. So I wholly rely on Yunus in terms of when he creates these materials to kind of give me an understanding of how that's going to perform if I need to manipulate that. But I work with pneumatics, hydraulics, electronics, coding, solid mechanics, fluid mechanics on a daily basis because I need to know those things so I can manipulate the actual material. But I need to know how that material is going to perform, so I need to understand the material science behind that. So materials as a whole, you need to know pretty much a little bit of everything, I feel. I feel like it's almost a jack of all trades to kind of process the materials. Obviously, you can be an expert in a particular material because, again, it's overwhelming just trying to think about if you're looking at aluminium or titanium or whatever. But yeah, I think it's many and varied.
Yes,
with materials, for sure.
I think that's certainly true across the board with materials. Many and varied, and as you say, constantly learning, always finding out new things. How about you, Mimi? Any final thoughts?
Do I have some final thoughts? Yes. Yunus has the best dungarees in the world consistently. This is what makes a material scientist. Also, material science is the best type of engineering. We will poach everyone because, as Will has said, it's a little bit of everything. Yeah. So you'd be hard or you struggle to find something or background in engineering or science that couldn't be applied to material science. I also think that you just don't get bored. I think the core thing for me to point out is, as a material scientist, you will start looking at the world differently. You will start looking at things being produced, being like, oh, was that cast? Was that hot rolled? Slightly annoying. You start looking at things and then you get really excited when things break. Like fracture. When things break and how they fracture, you could probably stare at that and you'll be that weird person watching something melt. But it's fun. And, you know, if you could do anything in the world, why not be someone who makes things break?
I think that's a brilliant place to end. So, yes, well, thank you all for all your comments. I think it's been a really interesting exploration of how we go about making samples, the challenges associated with that, how we then, once we've made them, you know, might look at applying various thermomechanical processing and the challenges associated with that. There are always more challenges, as we say, always more challenges, more things to explore. So for now, let me thank our two specialists on today's episode, Dr. Yunus Azakli and Dr. Will Pulfrey. Thank you both.
Thank you.
And thank you, Mimi, for joining us as well.
Thank you.
And finally, to our listeners, thank you very much for tuning in. Please do join us next time, where we'll be talking in more detail about advanced manufacture. Thanks very much for listening. If you want to join the conversation, you can find us on Instagram at Materials Unlocked. If you want to find out more about the topics that we've covered and the work that we do, a link can be found to our website in the show notes. Our thanks to the Advanced Metallic Systems CDT, the Henry Royce Institute, and the Department of Material Science at the University of Sheffield. See you next time.